we're going to use the Briggs-Rauscher reaction to talk about rates and how different chemical rate laws work to elicit some pretty interesting reactions and responses. So first of all, if we had three reactions here that were all tied together, reaction 1, 2, and 3, how could we write the rates for each of these? Well, remember that the rate, number 1 here, what is it based upon? Well, there is K, right? We always have K for each of these, but it's based entirely upon the concentration of reactant A. Remember, we're going to go back to collision theory here. So the more A we have in concentration, the more A there is to collide with one another and form the product for this step, which is X. So the higher, of course, the concentration of A is, the higher this rate is going to be. All right, so now let's look at the second one, rate 2. And rate 2 is, of course, another K. These Ks are all different, and it's based upon the reaction, the concentration of Y and X as well. And why is this? Well, this is because for this reaction to occur, an X and a Y have to collide with one another. They have to crash into each other for a reaction to occur. So we need both high concentrations of X and Y for the rate to increase. So lastly, looking at rate number 3 here, where would this rate law come from? Well, it would be entirely based upon the only sole reactant, the concentration of Y would lead this to form P, our product. So now that we have those three rates, if we started with all A, which is the sole reactant here, what would happen? And of course there's a little Y floating around at the beginning, or we couldn't start this reaction. So let's look at how this plays out. And I'm going to actually use a graph here, which is going to help us talk about the concentrations of these different reactants over time. So here is our graph. So first of all, when we have a lot of A, and I'm not going to put A or P on the graph until the very end, I just want to talk about what's going to happen here. Well, remember, the rate here is rate 1. And it's based upon what? Entirely. The concentration of A. And the concentration of A at the beginning is very high. So we're going to immediately start producing a lot of X. And so the concentration of X over time would look something like this, right? And so we'd have, at a certain point in time here, a high concentration of X. In fact, I could draw it even higher. We'd have over time here quite a high concentration of X. Now, eventually here, it's actually going to start tapering off because we're going to have a lower, we're using up some of that A, but something else really interesting is happening here. Look at what happens when we produce a lot of X. Look over here to the right, and we see as our X is a lot of X is produced here, but as we have a higher and higher concentration of X, we go into reaction 2 here. So rate 2, as we remember, is based upon what two concentrations? Rate 2 is based upon the concentration of X as a reactant and also Y as a reactant. So as our concentration of X, remember, has been increasing, we have a huge concentration of X now at this point, and we have some Y around, rate 2 is going to really start picking up because there's so much X around that it's colliding with Y very, very frequently. Well, as the X and the Y collide, they produce 2Y. So notice that even though we use up 1Y here, we produce 2 y's. So overall reaction 2 is actually going to produce y. So our y concentration over time here is going to look something like this. Now, what's going to happen to our X concentration over time? Well, as you look here, you notice that it's a reactant of this, and it's not a product. So we're actually using up X now. We have such a high concentration of X, it collides with Y, and we're using up X. Well, so that means that X is going to decrease in concentration. Now, I should have made it end a little lower. It's not going to go all the way away. It's going to kind of taper off right around there. Now, that happens because here, at the very beginning, R1 is going to dominate. Here, why is R1 still occurring? Of course, that reaction R1 is still occurring, but R2, because now we have so much X around, there's so many collisions with X and Y, that R2 is going to dominate. And don't forget, also we have so much X around that R1 is actually even going to slow down because there's more product, which of course pushes the equilibrium in the other direction. Now, at this point, right here, we now have quite a significant amount of Y, because as you look at the graph here, purple part, the graph Y is quite high. So when Y is quite high, concentration of Y is quite high, R3 is going to dominate. And when R3 dominates, we notice that R3, of course, is going to use up Y, right? So as R3 dominates, our Y concentration is actually going to take a significant dive, right? Because that is the only reactant of R3. Now, what happens as we use up more and more of this Y? We'll look at rate 2. Rate 2 is what was using up our X, right? So remember, the reason rate 2 dominated was because we had high concentration of X at first. Why does rate 3 dominate? Because we have very, very high concentration of Y. But if we notice here, what else does the rate 3 do? What is its job? It removes Y. As we remove this Y, what does that do? It slows R2 even more, right? As we remove Y, we have less reactants to collide, less Y to collide with X to produce reaction 2. This means, of course, that now we're not taking away our X anymore. Since we're not, reaction 2 is no longer taking away our X. That means we are going to have a resurgence in X. Because as rate 3 dominates, Y is gone, we no longer are losing our X. But of course, rate 1 is still, as always, producing our concentration of X. Now, as we move on from rate 3, here, we notice that once again, we've produced a lot of X, right? So let's look at what happens here. And by the way, we need to write rate 3 in here and show that it's based entirely upon Y. So that's why that's the one that dominates here where Y is high. Now, as we look here, we now have what situation? Let's break it down a little bit. At this point, we have high X concentration, and we have a little bit lower Y concentration. Well, because we have low Y concentration, rate 3 will not be going forward. Because we have high X concentration, rate 2 can now start colliding and producing more Y to refill that void because there's so much X around. So what is this going to do? It's going to lower our concentration of X, and it's going to raise our concentration of Y, right? So if we look at this process, it's fascinating because we see that these different reactions, because of collision theory, we see that the concentrations are actually switching places between X and Y. It's oscillating. This doesn't make any sense because we know that reactions move forward spontaneously and then cannot move backwards because that would be an unspontaneous process. However, if you look at the overall reaction, A is turning into P overall. And at the beginning, we have higher concentration of A, and we're slowly losing it. And over time, each of these reactions, Y is slowly producing P. Now, I'm going to draw it smoothly. Really, it wouldn't be exactly a smooth production of P, right? Because P would be produced the most when Y is being used up. So, of course, P's major production would be here where Y is being used up and here where Y is being used up. So really, if I was to be more accurate, it would look something like this. Right? It looks something more like that. But this is overall a reactant forming a product, which we know holds to regular chemistry. However, you can now see with the intermediates, there are oscillations in this reaction due to the concentration of reactants constantly changing. Let's look at what this produces, and after that, we'll come back and I'll explain specifically with not just X's, A's, and Y's, but what each reactant and product was that you saw occurring. To understand what was happening in the oscillating chemical reaction we observed, we need to look, first of all, at the overall reaction and then a couple steps and kind of break it down to understand. So first of all, the overall reaction, as we see here, takes IO3 and turns it into this I organic molecule. That's the reactant in red and then the product in blue. Now, this reaction has several steps, and a lot of these steps have a lot of more intricate steps as a part of them, but the salient steps here are steps 1 and 2. Step 1 uses this IO3 to produce HOI as a product. Now, step 2 consumes that HOI and produces our final product. Now, this doesn't exactly yet explain how it oscillates. We need to get into a couple more things for that. But as a brief background, if you look over here, whenever HOI is more than I concentration, you'll get an amber solution. And whenever HOI is less than I, we'll get a blue solution. Why? This actually is because I minus combined with I2 and then starch, which we have some starch in the solution, produces a blue color. This is oftentimes actually a starch test that's done in biology classes, but here we're using it instead of to show the starch, to show the I. So here we go. Let's look at some aspects of this that are really important. Well, looking at steps 1 and 2, we have to talk about a really important part of these, and that is that step 1 can happen 2 ways. Step 1 can happen through a very fast pathway, or step 1 can happen through a very slow pathway. The fast pathway actually utilizes a radical. So it has a radical mechanism and that's very, very fast. There's also a slow pathway, and this just uses a non-radical pathway, and it's much, much slower. So if we look at these two steps here, the fast and the slow, we'll notice that this reactant here can produce HOI very, very quickly if it's using the fast radical method, or produce it very, very slowly if it's using the non-radical method. Also notice that step 2 is consuming HOI. So we need to look at what the relative rates of all these reactions are to properly understand what's happening here. So if we look at the relative rates, we notice that the very fastest rate is the step 1 fast. So if it's running in its fast, which of course is the radical mechanism, if it's running in its fast mechanism, that is actually faster than step 2. Step 2, which we remember if we look right up here, step 2 consumes HOI. Step 2 is actually slower than the fast step 1. So if we put the other step in here, we'll notice that step 1 slow, which is of course the non-radical mechanism here, step 1 slow is actually slower than both of those. Now, if we look at what each of these are producing, we notice that HOI is our common factor here. So if we do step 1 fast, step 1 produces HOI, step 2 consumes HOI. Well, if step 1 fast is faster, so here we'll say step 1 radical, which is the fast method, is active and is faster, what we're going to have happen is, since it produces HOI, we're going to have HOI accumulating. Well, when HOI accumulates, interestingly enough, high concentrations of HOI produce I negative. Well, this is interesting because this step is a step in the non-radical pathway. And of course, the non-radical pathway is always going. So even right now, step 1 is dominating, the radical method is dominating because it's so much faster. But step 1 slow is always going. Well, the high concentration here of HOI combined with the water is going to produce Ri negative. As this goes, this I negative shuts off the radical pathway. This is a really key step. When this I negative accumulates because of our HOI, the radical pathway or the fast step 1 shuts off. This means that now we only have step 2 and step 1 slow going. So if only step 2 and step 1 slow are going, then we're going to say only step 1 non-radical, or the slow one, is active. That means that between these two, since step 2 is so much faster, step 2 now dominates. If step 2 dominates, that, remember, back to this again, step 2 consumes HOI, step 1 produces HOI. So if step 2 dominates, HOI here is going to be consumed. This means the concentration of HOI is going to actually be decreasing at this point. So we can see that HOI concentration is increasing and decreasing as step 1 or step 2 dominate, right? Because as the radical mechanism goes, step 1 dominates, we have more HOI. As the radical shuts off, step 2 dominates, and we are consuming HOI and losing its concentration. This means that we have a constant change in color, because if we look at this, it's amber when we have a higher concentration of HOI. And remember, HOI is made quickly by the radical mechanism. The radical mechanism makes HOI very, very quickly, so it gains a higher concentration, and we see an amber liquid. Well, we notice that the HOI is made slowly when the non-radical mechanism is going, and actually really the secret here is it's consumed by the step 2 process, which is now even quicker than the step 1 can make it by its slow non-radical mechanism. This means that we get a blue color because we have a much lower concentration of HOI than I negative, meaning I negative and starch give us our blue color. So if we look at this and look back at our reaction, again, we can see why it switches between blue and amber throughout this process. Now, is it going to do this forever? No, because over time, as you can see, we are consuming IO3 negative and making our product here. So over time, eventually, we are going to have only one color present because we're just going to have our product.